Thank you for joining us for our webinar on tips for teaching physics for the IB Diploma today. I'm Tamsin Hart from Cambridge University Press, and I'll be hosting this webinar for our speaker, Andreas Tsokos. While we wait for more attendees to join us, let me explain how we're going to run the webinar. We're recording the webinar today to share with you afterwards, so don't worry if your internet drops out, just rejoin us when you can. If you're having trouble with your speakers, we suggest using headphones or checking that your speaker isn't muted. Your microphones will remain muted throughout the webinar. If you have any technical issues or questions about our science products, please can you put those in the chat box and my colleagues will be on hand to help you. Please can you put any questions for Andreas into the Q&A box and our speaker will answer those at the end of the webinar. That's the end of our introduction. Just before handing over to Andreas, I'm going to share the results of the poll with you. At the moment, we've got quite a few participating. We've got 69% of you who have participated. Okay, let's end that poll and let's share the results. Okay, so what have we got coming out as the top challenges? We have got 43% on applying effective teaching approaches and preparing my students for assessment. Coming in below that, planning my lessons. Also, in fact, before that, we've got 40% on lack of time and time management. We know that is a big issue for everyone. And then following that, we've got following IB Diploma approaches. So that is really interesting. Thank you so much. So thank you for participating in the poll. And thank you very much for joining the webinar today. Now let me hand over to Andreas.
Thank you, Tamsin. And a very warm welcome to all of you for this webinar. I need to apologize for the hoarseness of my voice, but 2 days ago I tested positive for COVID. So I'm in a rather low energy state today, but we will manage this. So the photograph of King's College, Cambridge is here to say thank you to our host today, Cambridge University Press. But it is not a photograph intended to imply that IB Physics is an elitist course. I never believed that it was elitist. I think it is a very accessible course to most high school boys and girls. So let's talk a little bit about the new IB Physics course. I'm going to split this webinar into 3 parts. In part 1, I'll talk briefly about the changes in content and assessment. I say briefly because we now have the guide published, we have specimen papers. A lot of people have posted comparisons between the new and the old syllabi. So I will be brief there. In part 2, I'll talk about how the Cambridge resources help in teaching the new course. And for parts 1 and 2, I'll be doing most of the talking, unfortunately, but then we have part 3, in which I hope to have a more interactive dialogue with all of us. And I'll be talking about these buzzwords that are popular now: inquiry, conceptual understanding, critical thinking, and creativity. And how does one foster the conditions in day-to-day teaching that promote these ideas? So let's start with the new guide. There are new groupings. The material has been grouped into 5 units, each unit being dominated by a particular idea. So, and the obvious ideas are obviously here: space and time, and the relation of force and motion, the fact that matter is made out of atoms, and so on. I say new because in quotation marks, because that's more or less what we have in the present guide, the old guide. The only real difference is that in Unit B, the new guide has introduced electric current and circuits. Other than that, it's the same kind of grouping that we've had in the past. So what are the changes in content? I estimate that the material removed is approximately 25 hours worth of teaching, which along with the 25 hours at high level from paper 3 that we gain now that there is no paper 3, we have a reduction of approximately 50 hours. And this is the material that has been removed. Polarization, details of cells, Kirchhoff laws, the current equation. The current equation is actually a bit of a mistake, in my opinion, since we have put in unit B the particular nature of matter. We put circuits in there. It would be nice to have that equation that shows a particulate nature of electric current, but it's been removed, but that's okay. Energy production has all been removed, resolution, thin film interference, all the particle physics, capacitors, diode, rectification circuits, transformers, Heisenberg principle, pair production, annihilation, tunneling, and wave functions, they're all gone. Some material has been added. I estimate approximately 40 hours worth of teaching. I indicate this in 2 colors. The material in white is material that has come down to the core from the present options, like the buoyant force, stellar evolution, HR diagrams, luminosity and apparent brightness, parallax, rotational mechanics from option B, special relativity from option A. But then there is also some brand new material like Stokes' law, the equation for thermal conduction, phase angle, the Millikan experiment, electrostatic induction, Kepler's laws, the formula for magnetic force per unit length, and for high-level 2-dimensional collisions and Compton scattering. So roughly 50 hours have been gained, 40 hours have come back in, but remember that units, measurement, errors, and uncertainties, uncertainty propagation, scalars, and vectors are no longer part of the guide. They have been relegated to mathematical prerequisites, but they need to be taught and they will be examined. So this 50-40 hour comparison of the previous slide may not be very accurate in view of this. So the bottom line is that the volume of the present, of the new guide, is not particularly reduced, in my opinion, compared to the old. So that means we are still faced with a very large syllabus to go through. On the positive side, I think there is very little that is abstract in the SL guide, in the SL syllabus, so that should be easier to teach. Let me now go to the changes in assessment. As we all know, there are no longer option topics and therefore no paper 3. For paper 1, we're going to have a section A with multiple choice questions, just like we do now, except that there will be 25 questions at SL and the same number, 40 at HL, as previously. But now we're going to have a section B with data-based questions, questions similar to what we have now in section A of paper 3. And the other difference is that a calculator will be allowed on both sections of paper 1. In other words, the multiple choice questions will allow a calculator. Paper 2 will consist of section A with short questions from throughout the syllabus, and a section B with long questions. Each will be worth 20 marks, so that's quite unusual for the IB exams. There will be one such question for SL, which will be common with HL, and HL is going to have an additional high-level question. I don't know if you noticed a discrepancy between the guide that has been published and the specimen papers. The guide says that the paper 2 standard level is worth 55 marks. The specimen paper has it for 50. So that is something that needs to be decided by the IB. Will it be 50 or will it be 55? Also to be decided is another issue concerning these long 20-mark questions. Can this question be made entirely from material from one unit of the 5, or must it be a combination of 2 or more units? That is also unclear. And I believe that the IB will come to a decision about these issues by the end of April. Another change is that the number of command terms has been drastically reduced. Objective 1 has gone down to 2 from 7, Objective 3 down to 8 from 22. And I think that's a good thing, because it means that there's less command terms to explain to students, because it's very important for the student to understand the meaning of the command terms, because that determines the amount and detail and depth in the answer. So the fact that there are fewer of them is a good thing. I now go to part 2 of this webinar about the resources that Cambridge University Press has come up with. Each chapter begins with guiding questions. For example, what is a wave? How do waves transfer energy? What is oscillating in an electromagnetic wave? So these guiding questions at the beginning of each chapter define the problems and the questions that need to be resolved in that particular subject, in that particular chapter. And every chapter has one such box at the beginning. Another new feature of the book is what I'm calling check yourself questions. These are questions interspersed throughout each chapter. There are about 5 or 10 such questions in each chapter with answers at the back of the chapter. And these are very basic questions that need to be understood by the student before he or she goes on. So, for example, look at this standard one here, check yourself 1. It's the standard question of a ball hitting a vertical wall and bouncing back, and you ask about the magnitude of the change of the momentum. And as we all know, most students will make the mistake of missing the minus sign due to the vector nature of momentum. So these are very basic questions that test for understanding and control, if you like, for the student, the passage to the new material. As with the old edition, there are lots of exam tips that indicate common mistakes, common misconceptions, misunderstandings, as well as hints about how to approach a particular solution to a problem. Like, for example, here I referred to the graphics display calculator that all students have because mathematics courses require it. It's an expensive piece of machine. Why not use it in physics anytime we can? And there are many situations in a physics setting where the GDC can be used very efficiently. Key points, definitions, the main laws, main concepts are also highlighted, so there is easy reference to them. And as with the previous edition, the new textbook is full of worked examples, examples that clarify certain situations, describe ways to solve problems, problem-solving skills. There are lots of such examples throughout the book. Also, lots of end of chapter problems. Some of them progressively getting more difficult as we get towards the end of the chapter. And some more challenging, like I say, and some more challenging problems at the end of the chapter. If you look at here, number 37, I asked the student to go and do some research on their significance. I'm talking about the Planck length and the Planck time. So on many occasions throughout the book, I do refer to literature or guide the student to go and do some more research and find out some more information about a particular topic or a particular subject that I think is interesting, or I think that the students may find interesting. And all these problems have detailed solutions and not just answers. And these solutions are in the digital edition of the book. And the digital edition comes along with the book in print. We are lucky in physics in that there is no better place to talk about theory of knowledge. Physics is the natural place to discuss TOK. Practically every aspect of physics is TOK. So the textbook is full of boxes commenting on connections between the material of a particular subject and TOK. Where do laws come from? Why was the Bohr model accepted, even though there was no theoretical evidence in its favor? Are fields real? And all kinds of similar questions can be discussed with great profit, I think. And we should obviously make every effort to include TOK as part of our teaching. NOS stands for Nature of Science. Again, the book has lots of boxes about the nature of science, the nature of the scientific method, models, the limitations of models, and so on. But for me, NOS is more appropriately standing for the nature of scientists. And I find this really interesting and exciting aspect of the course to introduce and talk a little bit about the nature of scientists. And what I mean by this is take the example of Doppler. We introduced the Doppler effect in 1842. The effect was not at all received favorably. It took years and years before there was solid experimental evidence in favor of the Doppler effect. And in fact, Doppler was attacked by his colleagues at the Austrian Academy of Sciences that he had to resign his position, leave Austria, and then in depression and sickness, die a few months later in Venice. So here's an example of a person who could not handle that enormous pressure that was weighed upon him. Whereas at the same time, we have the case of Chandrasekhar, who was also publicly ridiculed for his work on white dwarf stars, ridiculed in fact by his own mentor. But unlike Doppler, he stuck to his guns. He believed in what he did. He showed the resilience, the perseverance that we want to see in our own students. And Chandrasekhar, of course, became one of the greatest and most influential astrophysicists of the 20th century, with a Nobel Prize to show for it. And Fresnel's story is also a very exciting and interesting one. Then we have boxes of science in context, which show how a particular topic that we are discussing has real-life day-to-day applications. Typical example, the GPS system, and how its extraordinary accuracy depends on corrections from the theory of relativity, even though the speeds of the satellites are tiny compared to the speed of light, yet that tiny effect of relativity is a real effect, and without it, the GPS system would not be much worth. And the Doppler effect also, and its application to medicine as well as radioactivity applications. Lots of boxes like this showing science in context. The textbook has some extension material beyond the syllabus, beyond the guide, material that will not be examined. Why is it here? It's here because I find it interesting. I think students might find it interesting. So here is an example about nucleosynthesis and the reactions that lead to the production of elements inside massive stars. I've also included a bit on gravitational waves, because the 2015 discovery by LIGO of gravity waves is an extraordinary technological as well as physics innovation, and gravitational waves are in the news. People might like to know a little bit more about it, so I have a short material on it. The guide, the new guide, is published by the IB, has a lot of what they call linking questions. In this textbook, I call them links, and links are supposed to be connections between different parts of the syllabus, different parts of the guide, connections that show that similar concepts, similar skills, similar techniques, similar principles apply to different parts of the guide, and therefore that connection can be used with profit in making understanding better. Okay, I call this slide references to literature, and I am going in a bit of a tangent with this slide. This is a Nature of Science box in which I refer to Quanta magazine, and I want to advertise Quanta magazine. It's a free magazine, it's electronic, comes out every Friday, and it is a fantastic way to keep up with developments in mathematics and physics and chemistry, biology, computer science. It is a great magazine to have if you are running a journal club with your students, where students present material that they find interesting. Quanta magazine is a great source of interesting stuff to do. And Quanta magazine is funded by the Simons Foundation. And here is Mr. Jim Simons, a professional mathematician who has made a huge contribution to physics by discovering something known as the Chern-Simons term in quantum field theory. Of course, Jim Simons left academia many years ago and started a hedge fund company. He is the world's richest mathematician and one of the richest men in the world because of his company that is applying mathematics and physics to Wall Street. So that was just an advertisement for this magazine, which I really like, and I think it's really worthwhile. Okay, there are more resources in the digital edition, which, as I mentioned before, comes along with the book. The digital edition contains mock specimen papers and mark schemes, additional exam-style questions, 500 multiple choice questions, 100 for each of the 5 units, database questions, a chapter on measurement, uncertainties, and vectors, full detailed solutions to all the problems. I apologize for coughing all the time. Guide to the internal assessment. There are lots and lots of ideas about IA projects, and there is a very long list of things to do and things not to do in the writing of the report. And also there's a guide to the external exam with hints about how to approach it. Teacher resources is another resource for teachers only. So students are not supposed to have access to this. And this contains lesson plans, ideas for teaching, ideas for differentiation, ideas for reflection, discussion of common misconceptions, ideas for homework and class activities. It has 35 quizzes, and it has this a collection of these long 20-mark paper 2 section big questions that the IB is calling deep dive questions. So this is for teachers only. And finally, Cambridge University Press is also publishing a workbook written by Mike Farrington, which is a book of questions and problems that complement the other textbook. And yeah, I believe these are the resources that we have produced at Cambridge University Press. Obviously, there are other publishers around, other books around. You must find the one that you're comfortable with. I now come to the third part of this webinar, featuring these words: inquiry, critical thinking, creativity, and conceptual understanding. The numbers have to do with how many times these words appear in the guide, the new guide. So inquiry appears 24 times as opposed to 10 in the old guide. Conceptual understanding 17 times as opposed to 4. So it's clear that this is the way the IB wants us to teach IB physics. Obviously, a lot of people have been teaching this way for years and decades, way before these words became popular. But obviously, the IB wants to see evidence that we're actually doing it. So if your school, for example, is up for evaluation, the IB people will want to see evidence that this way of teaching is present in your documents. So it's something that we have to move towards if we're not already doing it. So, so inquiry-based teaching and learning is the heart of IB pedagogy. And what this means is that the student has a central role in the learning process. The student is not supposed to be memorizing one fact after the other. The student is supposed to be actively engaged in learning, actively inquiring about things, researching, asking questions, sharing ideas. And the role of the teacher correspondingly, therefore, is not just to provide one fact after the other, but rather to engage the students by triggering their curiosity. So the big question, of course, is how does one do this in practice? How does one implement these ideas? How does one foster these conditions in day-to-day teaching? One way that I'll present here is something that I have tried, and there are obviously other ways as well. But one way is, imagine that you have split your class into small groups of, let's say, 3 or 4 students. You give them a task. It could be theoretical, it could be experimental. And you, as a teacher, you go around from desk to desk, from group to group. You participate in the discussions. You give hints when necessary. You correct when necessary. You listen. And the point of each task would be to precisely start the discussion between the students that will force them to inquire, that will force them to be creative, that will make them more understanding of the basic concepts in physics. So what I want to do now is, and here I hope to have some interaction with you, is to give a few examples of tasks that might achieve this. And here's my first one. And this one has a large container of water which is being heated from below. So the water in the large container is boiling. And then you take a smaller container of water. The water here is about, let's say, 85 degrees Celsius, 90 degrees Celsius, and you place it in the big container. And then you ask the question, will the water in the small container come to a boil? And you expect the groups of your students to try to answer this question. Will it come to a boil? Why? How? Will it not come to a boil? Why not? What is the problem? I don't know. Is it possible to stop here for a minute and see what do people think? I mean, what is going to happen to the water in the small container?
If you'd like to add your answers to the chat, Andreas will be able to see them.
Yeah.
Oh, we've got answers coming through. It will overflow. It will not boil. Reach boiling point, but will not boil.
Very good.
It won't boil. No, it will not boil.
Okay.
We have a consensus coming through. It won't boil. No, I don't think it will boil, but it will reach 100 degrees.
That's correct, yes.
Get warm or hot.
Yes.
It will heat, but won't boil.
Right.
Yeah, definitely a consensus coming through there.
Yeah, exactly. But someone says it will boil. The point is, do we see the relevance of a question like this when it comes to conceptual understanding? For example, we teach in thermal physics that the direction of heat flow is determined by temperature difference. So heat always flows from hot to cold to colder. So obviously the boiling water being at 100 degrees is at a higher temperature than the initial temperature of the water in the small container, and therefore heat will flow from the boiling water into the water in the small container, raising its temperature to 100 degrees. But now we have an equality of temperatures, and therefore no more heat can flow. But we need more heat to flow, because if the water is to boil, we have to provide the latent heat of vaporization, and we just can't provide it. So it won't flow, it won't boil. Here is another question that I have used in class. Why does temperature stay constant during a phase transition? Ice melting into liquid water, for example, at 0 degrees Celsius. Why does the temperature stay constant? We have asked this question in IB exams many times. And the official answer of the mark schemes is that we explain this by saying that the energy we provide goes into intermolecular potential energy and none goes into random kinetic energy. Since no energy goes into random kinetic energy, the temperature cannot change. I don't know if you agree with me that this is a tautology and it's not a satisfactory answer. I mean by this that temperature and average random kinetic energy are essentially the same thing. So saying that no energy goes into random kinetic energy is like saying, oh, automatically the temperature doesn't increase. But why? What is it that prevents energy from going into random kinetic energy at the melting point? I think this discussion of this question is a very useful discussion that also is related to heat flow and the direction of heat flow of the previous slide. Okay. Okay, for a group of physics teachers, these are kind of obvious things. A very useful thing to discuss is the standard example shown here, a cart moving to the right, a spring pushing a ball vertically upwards. The question is, where will the ball land? Okay, that's an easy one, but a very useful exercise in class for students. This is one of my favorites. We have two towers of equal height. A red ball is launched horizontally with speed v. A blue ball is allowed to fall vertically in the absence of air resistance. Which ball lands first? Can we understand this conceptually? Can we understand this without going into mathematics, without going into the equations? We can very nicely if we go to a frame of reference of this observer over here who is moving to the right with velocity v, the same velocity as the one of the red ball of the previous slide. But now, as far as this observer is concerned, the red ball is just falling vertically down and the blue ball is coming at him at the same speed v as the blue ball in the previous slide. So the situations have been completely reversed, and therefore by symmetry, the time has to be the same.
We have some thoughts coming through in the comments, Andreas. We have both
Right.
land at the same time.
Yes, both land at the same time. The question is to try and explain this in as conceptual a way as possible, without mathematics, without formulas. This is another case of where I ask students to make use of their expensive GDC. In physics, we have a situation, we could discuss this when we do waves and refraction. We have a situation where someone can run in this orange region with speed 3, but in the blue region, they can also, they can only move at a speed of 2, and they need to get from A to B in the shortest possible time. Then students can use their GDC to find, well, algebraically, they can easily find the expression for the time taken to go from A to B as a function of this distance x. They can plot this time as a function of x, and they can find the minimum of that function that will give them the required distance x that whoever is doing the running has to cross the boundary in order to get to B. And what will they discover by doing this is, of course, Snell's law. So what they have discovered here extends to Snell's law and says that light, exactly, Fermat, leading to Snell. Okay, now let's go to this example here, where longitudinal waves are always a big puzzle to students. They're confusing. They're confusing because what we see here, this red sine curve, is just an abstract mathematical representation of the displacement. It is not something that you see. If it was a transverse wave on a string, you would actually see the string shape following this red pattern, but not for a longitudinal wave. So here is a task involving this graph. What is the distance between points P and Q? P and Q at positions 0 centimeters and 10 centimeters are the equilibrium positions of 2 points in the medium. At time 0, this is the longitudinal wave in the medium. What is the distance separating P and Q at time 0? Okay, that's an easy one, but I'll extend it in just a little bit. Obviously, what's the distance, anyone? The distance between P and Q is 14 centimeters, of course. So they have to understand that P has 0 displacement according to this graph, so its position is at its equilibrium 0. However, Q at 10 centimeters has a displacement of 4 plus 4 centimeters, so it has moved 4 centimeters to the right. Therefore, the distance separating P and Q at time 0 is 14 centimeters. Now you ask, all right, what's the separation between P and Q a quarter of a period later, half a period later? You ask the students to think about that. That will force them to see what a longitudinal wave means, what the displacement in a longitudinal wave means. And if you really want to stretch them, and again, the calculator here can be of great help, even though if the students are taking high-level math, they can even do this analytically. You can stretch them by asking, what is the maximum distance separation between P and Q, and what is the minimum separation between P and Q? Yeah, you say, Prita, that this is a great question. Yes, I think it's an excellent question to really get students to understand all kinds of things about longitudinal questions. For example, one approach is to realize that if we go to particle P, particle P is doing, of course, simple harmonic oscillations as the wave passes through the medium. And the new guide is very specific about how we find the equations for the displacement in simple harmonic oscillations using the phase angle. And it's not too difficult to see that the displacement of P will be something like 4 sine omega t, whereas the displacement of Q would be 4 cosine omega t. And therefore, the overall distance between P and Q is just the 10 centimeters plus 4 sine omega t plus 4 cosine omega t. And students can now either work on this analytically, or they can put it on the calculator to see the maximum value of this quantity. And they will find that the maximum value is 14 is 10 plus 4 square root 2 or something like that. But it's a great exercise, in my opinion, of visualizing and conceptualizing what a longitudinal wave is. This is also one of my favorites. And qualitative thinking. This question is very difficult to solve mathematically with equations. So we're not going to use equations. We're not going to use mathematics. We're just going to use basic understanding of the laws of magnetism and electricity, and nothing more than that. So what do we have? We have a uniform magnetic field shown in arrows, green, directed along the z-axis. And we have a uniform electric field directed along the y-axis. At the origin, we have a positive charge, which is released from rest. What is the path of the charge? We don't want equations, we just a qualitative description of what that path should be, without much math, without much many equations. Do you want to have a go? Do you want to just a rough guess? What do you think this charge is going to do if you release it from rest?
Yeah, we have answers coming through here. Spiral yes. On the y-axis, x-axis.
Right. Yes, the charge helical path along the x-axis. Okay. If you start thinking about this, it's obvious. No, it will move. It will move. Initially, the velocity is 0, so the magnetic field exerts no force, but the electric field does. So the charge will start moving out along the y direction, picking up velocity. As soon as it picks velocity in the y direction, there will be a magnetic force towards the x direction. So the charge will move on the xy plane, bending like this. At some point, it will keep bending. I don't know if I can draw this a little bit. It'll come out, it'll start bending like this. And at this point, the electric field will stop accelerating it. The electric field has been accelerating the charge all along from the beginning, from the origin to this point. But now, because of the bending of the path due to the magnetic field, it's going to start going down like this. And now the electric field is decelerating the charge. And by symmetry, whatever speed it picked up is now going to lose. So by the time you reach the x-axis, your speed is 0. And then the problem begins again. It gets repeated. So the motion of this charge will be a path, a curve like this that repeats on the x-axis, and the motion is entirely on the xy plane. And that's all you require of a student without math and without equations. It turns out this is just a cycloid. It's a cycloid on the x-axis, and with a little bit of more work, you can see that cycloid motion is circular motion, which is what you expect if you're in a magnetic field, but with a drift velocity due to the electric field. Anyway, this is a purely qualitative question that can be answered with some thought and with some guidance from you, the teacher, but these are possible things for students to answer. And I do believe that they do contribute to what we want to achieve with conceptual understanding and creative thinking and so on. I'm running out of time because my voice is also slowing me down. Maybe I'll of course send, when we send out the recording, this will come along with it. I have lots and lots of other examples. For example, the new guide says we should be discussing how much rocket fuel we need to go from one orbit to the other. Here's a very doable example of the International Space Station is losing height. Because of friction with the upper atmosphere, and this kind of calculation enables you to calculate all kinds of things. How much is this frictional force? It's surprisingly small. How much fuel do we need? All this can be calculated from a graph like this and basic knowledge of the syllabus. So I won't discuss all the other examples that I have. I'll leave those for some other time. Let me just close with this. The new guide says that we should be, it's allowed for students to collaborate in gathering data. So one nice example where people can collaborate in getting data is this investigation of a funnel that's filled with granular material. And then you ask the question, how long does it take to empty the funnel? How does that time depend on variables such as the density of the material, the diameter of the opening of the funnel, the angle theta of the funnel, the height of the material, and so on. And the only reason I'm mentioning this is because I asked ChatGPT to tell me how does the time depend on the diameter of the opening. And I was hoping to get a formula. Didn't give me a formula, but it did give me this answer. Actually, it's a longer answer. I've cut parts of it out. But if you read what ChatGPT says here, it's giving the student all the variables. It tells you all the variables that you need to consider. What else does it tell you? It tells you that, hey, the relationship may not be so simple as you think because, here's something to include in your evaluation: the size and shape of the granular material. So make sure you talk about this in your evaluation, and ChatGPT has just told you about it. It also tells you, the flow rate, the amount of mass that leaves per second may not be constant. Most people doing the experiment assume a constant flow rate, but now you're being warned that that flow rate may not be constant. So maybe what can you do in your design of your experiment to control the flow rate? And how can you make sure that it's constant or not constant? Anyway, that's something to bear in mind. ChatGPT is wonderful. I wouldn't disagree with that. I apologize for taking so much time, but like I said, I was forced to go a little bit slow because my throat is not in its best. But I thank you very much for listening to me. And now I guess, Tamsin, we go to questions. How do we do that now? Yeah.
Thank you. Thank you, Andreas. We're now going to move on to the questions.
Yeah.
So thank you also for talking through your cough. It was really appreciated. It was a fantastic presentation. So are there any further questions that we can get into the Q&A box before I begin reading through? I'll just give you a moment to put your final ones into
I can start answering. I can start answering the questions I see in the chat. Yes,
brilliant. I will read those out to you now.
Good.
Lovely. So,
okay.
What are the changes to the IA? Are there any mandatory labs to do or changes to G4P?
The IA has changed only in the sense that there are fewer criteria. There are only 4 criteria. Apart from that, there is no other change.
Brilliant, thank you. Will there be pages in the textbook dedicated to the mathematical tools such as units, vector mathematics, and uncertainty propagation?
Yes, there is a full chapter covering this material in the digital edition that comes with the book.
Brilliant. Will the data-based questions require knowledge of particular practicals? I believe there are no longer required practicals. So will these be purely data analysis questions, or will they require knowledge of certain practical techniques?
You're absolutely right. There are no more prescribed practicals like in the previous syllabus where we had a list of them. So that means that the database questions will rely on basic lab skills like propagation of errors. It would be a very common thing. Error bars, getting intercepts, getting gradients, and also good practical skills that should have been developed in a practical program. But no reference to particular experiments. Any experiment would be fine and could be included.
Brilliant, thank you. Given the anticipated time difference and constraints of a large syllabus, what impact do you foresee in the provision of practical work for students to support development of practical skills?
That's a tough one. I mean, obviously, students should enter the IB program with some awareness of a practical program before they enter the IB. Having said that, though, yes, the syllabus is large, but it does leave time. In fact, in my opinion, it leaves enough time for a good practical program to be developed that will develop the skills necessary to do well on the IA. And it's a mistake to think that just the practical program consists just of the IA. It would be a disaster if it's just the IA. There should be a good, solid, practical program that develops the skills necessary, builds on the skills from the previous years in order to make it possible to do a decent IA investigation.
Brilliant, thank you. Now, the next question. Given the large number of problems available, how do you decide which are the most illustrative ones to be solved in class? Also, typically, how many?
The more, the better, is my general rule. The more, the better. I would say for every set of questions, for every problem set, I would say half, at least, is what you need to do in order to really make sure that you have mastered a particular topic. Because the problems that I have in the textbook don't tend to repeat. In other words, I don't have the same question asked 10 different times. They tend to be different. So I would say half of them is a good guess.
Great, thank you. Now, how can teachers manage group data collection for IA?
What do you mean by manage? I'm not sure.
Douglas, are you able to put anything in the chat for us about what you mean by manage? While we're waiting for that, let's move on to the next question,
Well,
and we can come back.
I can say all that the IB is saying is that a group of 2, 3, 4 students can work together, designing apparatus, for example, putting it together, setting it up, and using it to collect a huge database, a huge number of data from that setup. And then what the IB is then saying, the students involved in that collective data gathering have to select different variables to investigate. So the collection of the data may have been common, but the analysis and the variables involved will be completely different. This is what the teacher has to make sure that happens.
Lovely, thank you. And then our final question, unless there are any more anyone would like to add to the question list. So we are free to do practicals from the topics just for a better understanding of the topics.
Absolutely, absolutely. You can do practicals that are carefully designed to develop the skills that we need to develop in order to do a good investigation, the IA. In other words, yeah, any practical is welcome.
Now, lovely. We have 2 further questions
Yes.
that have come in. Could you please give us some information about paper 6, i.e. the alternative to practical?
Paper 6 is not part of the IB, it's part of the A-levels.
Yeah, okay. Let's move on to the next question. Is there an internal assessment cover sheet like 4/PSOW form?
I think there is, but I am not 100% sure on this one, but I think there is.
Brilliant. And I think that's it for all the questions today. That's fantastic. So thank you so much, Andreas, for your fantastic presentation today and stoically continuing with your cough. It's really appreciated. And thank you so much for everyone for attending today. To find out more about the resources discussed today, please speak to your sales representative or visit cambridge.org/education/science. My colleagues have been putting some links into the chat as we go through, linking specifically to our IB Diploma Physics resources. Good luck with your teaching and goodbye.